Hey Dustin, I've got a new project for us.
All right, what is it?
So, a little while ago, my cousin lost his arm, and he works in a warehouse, and he decided that he wants to build his own prosthetic arm. The problem is that working in that warehouse, he has to lift 50-pound boxes all day long. And he's not like the richest guy in the world, so he wants to make his arm pretty cheap.
So it wouldn't cost him an arm and a leg?
Oh my goodness. Yes, so it won't cost him an arm and a leg. But he wants us to make sure that he has enough infill in his arm so that his arm doesn't bend and break.
All right, so it sounds like we needed some tensile testing to find the right infill material.
That sounds great. Let's get to it.
The machine that we got to test the samples is called a Tensile Tensile Tester, which has a max hex capacity of 50 kilonewtons with an accuracy of 0.5.
To record the length and thickness, we're going to be using digital calipers with an accuracy of 0.1 milli-inch.
The expected outcome of our experiments is the determination of the Young's modulus of the PLA specimens with different infills, based on the stress-strain diagram. These are the key concepts that we're going to use. Firstly, to quantify the total uncertainty, we use the RSS method, which is based on the bias and precision error. Moreover, we apply uncertainty propagation to obtain the total uncertainty, the modulus of elasticity. Since our sample is smaller than 30, we use a student state distribution to analyze our data. To remove all outliers, we apply Chauvin's criterion, and chi-squared analysis help us verify that our sample is a Gaussian distribution. In order to obtain the Young's modulus, we have to measure variables like the force from the tensile tester, the width and the thickness of the specimen, and the initial and final length of the specimen with a caliper. For the 10% infill specimen, the Young's modulus is 633 megapascal. That is going to be the lowest value, because when the infill goes up to 100, the Young's modulus is going to reach around 3000.
I think that the higher the percentage of infill goes, the more elastic it'll be, because there's more material there to resist just this brittle break that we have.
In our tensile tester experiment, we are trying to figure out how the modulus of elasticity changes with different infill percentages in 3D printed specimens. However, like any experiment, there are going to be sources of error that could mess with our results. First, we have systematic errors, which are biases that can cause consistent mistakes. If our load cell or extensometer wasn't properly calibrated, every reading might be slightly off. Also, 3D printing isn't always perfect. Things like filament inconsistencies or slight temperature variations in the nozzle could introduce small but consistent differences in our samples. Likewise, there are random errors which affect precision. These happen due to things like slight misalignments when setting up the test, minor variations in strain rate, or even environmental factors like temperature changes. These errors don't shift results in one direction but make them less repeatable. To keep these errors in check, we're taking a few steps. We are going to calibrate our equipment before testing to reduce bias. We have kept print conditions consistent to minimize variation in specimen quality. We are running multiple trials and averaging results to smooth out random errors, and we have controlled environmental factors to keep external influences to a minimum. By being aware of these potential errors and taking steps to minimize them, we can get more reliable and meaningful results.